All right, let's go and get this started. The microphone does not want to work, so I guess I'm just gonna have to be a little loud, but that's okay. All right, can everyone hear me okay? Yeah, just volume good. If you can't hear me, just raise your hand at some point and tell me, and I'll try to speak louder. Yeah, everyone online, you can hear me, correct? Another test there. Somebody online confirm that they can hear me, please. That's yes. Can somebody online say something so I can see if the speakers are working?
Yes.
Fantastic. Thank you. All right. Lower this. So once again, welcome to another linear algebra review session. My name is Zach. I'm one of the TAs for this class. I TA Friday mornings for section 3. First year PhD student, studied math and electrical engineering in my undergrad. Here I am, lo and behold, last exam. Hooray. Cool. So before we get going, just to talk about the actual logistics of stuff. Your exam is Wednesday night, correct? What time is the exam? Yeah. Not great, but it's 8 to 9:15. Make sure I have that proper. Yeah, 8 to 9:15 this Wednesday. I have another office hour tomorrow from 1 to 3, and there's a bunch of other TAs that have office hours as well. I'm in the math lab in the Colk for that. And yeah, we'll do this in the same format that I've done my last few reviews for those of you that have watched those or been to those. I'll kind of go over like a general view of everything, and then we'll start doing some problems and actual like quantitative stuff. So just kind of take that as questions happen. I'll talk about some broad stuff as we need it more so. So someone will ask me a question, diagonalization. I explain everything about diagonalization, and then we go from there. This exam, I believe, starts with determinants, and then it ends with diagonalization. Double check on that. Good. Oh, complex eigenvalues right after diagonalization. Okay. Yes. So some notes that I will just say as little like sidebars of things to remember that you might not. That might not be on your list of things to remember for this exam. The quadratic formula is something that every Georgia Tech student should know, business major or not. It's not going away anytime soon. You'll have to use it probably until the day you graduate if you're a STEM major. If you're a business major, then yeah. Anyways, quadratic formula and also the unit circle. Because there's, yeah, I know. Ooh. But there's usually like on the last exam, they'll have like rotation questions and stuff like that. All right. And if you want me to reteach the unit circle real quick, I can do that. But yeah. So any questions about any other big picture stuff before we get going? Everyone knows the rooms they're going to for their exams, or will know them, where to check them, everything like that. Cool. All right. All right, what questions do we have? And this can be something like, what the hell is an eigenvalue? Or how do I take a determinant of a 4x4? Or what is cofactor expansion? Or anything along any of those lines. To something more specific like midterm this semester at this question. Yeah. Geometric multiplicity and algebraic multiplicity. Sure. Okay, so this ties back to the concept of diagonalization, okay? And that boils down to what I like to just call CDC inverse decomposition. And this class is the only kind of decomposition we learn. In classes like 1554 and 1556, we learn a whole slew of other ones as well. But this is the main one we focus on, okay? So we have C is a matrix. C is an n by n matrix with n eigenvectors. Okay, and D is an n by n diagonal matrix with n eigenvalues on the diagonal. And the most important thing to note here is columns of C correspond to columns of D. Okay, and what that means is if your second column in D has lambda equals 2, your second column in C will have the eigenvector for lambda equals 2, okay? They line up vertically just so you can keep all of like your ducks in a row, all right? So how do we find this? Well, to find algebraic multiplicity, we have to take it back and talk about eigenvalues, and then we have to go and build upon what eigenvectors are and everything like that. So what is an eigenvalue? Anybody have a textbook or general definition? I know it's a big lecture, but yeah. Exactly. Not necessarily a real number. It could be complex, right? So an eigenvalue, which we just denote as lambda, all right? What we define it as is some number that we call lambda, such that a times some vector is equal to just lambda times that vector. Okay, what that means is if, like, an example of why we like to do this, for example, is if A is 30 by 30 and V is a 30 by 1 vector, you don't want to do that giant matrix algebra, right? And if lambda equals 1, you can just skip all the matrix stuff and just say it's equal to 1 as your vector. All right, that's the whole motivation. Also, for any of you that have to take any differential equations class, this is going to be something that you're going to have to remember and practice and use with calculus. Yeah, I know, it only gets better from here. But of all the things in linear algebra, the thing that you should remember how to do or know how to do the best is eigenvalues, eigenvectors. Okay, those are the big two for engineers. All right. So this is the definition of an eigenvalue. Another proper definition is some lambda such that A minus lambda I, the determinant of it rather, is equal to 0, which is equivalent to saying such that A minus lambda I has linearly dependent columns. If it has linearly dependent columns, what else does that mean? Yeah. Yep. This implies that A minus lambda I has at least one free variable. I'll just say free variables in general. Free variables. What else does it mean? What does it mean if you have a free variable? It has a null space, exactly. And this means it has a null space. Right? Because if the determinant is equal to 0, you know that it's not invertible. When it's not invertible, it has a null space, right? So this is kind of a whole stretch of things together that just goes to say that we define eigenvectors as our V, such that AV equals lambda V for some V, for some lambda. And how do we find these? Well, we find these by taking a basis of the null space of A minus lambda I for each lambda. Okay. Is this making sense? Are there any questions on this so far? I know this may not be the textbook definitions you were shown, but this is the way that I think makes the most sense. Okay. Please ask a question if you have it, because if you do, someone else definitely has it. Okay. And I promise I've heard a dumber question than any of you could ever ask. Okay. So this is just me saying, this is just your last exam, right? Finding bases. Okay. And how do we do that? Just as a review, to find this, find A minus lambda I, then you put it in parametric vector or row reduced echelon form of A minus lambda I, and then you put it in parametric vector form, and then you have your basis. And this is just your eigenvectors. I know that's a very long process and there are some shortcuts from stuff, but this is how you rigorously find eigenvectors for any eigenvalue for any square matrix. Okay. So this is how we find them. Okay. This is the broad, like, I can almost guarantee on this exam, right? You're going to be saying, they're going to give you a matrix and say, find the eigenvalues, find the eigenvectors, find CD, right? So this is something that you should know how to do. Yeah. It is not invertible. Exactly right. That's the whole point of eigenvalues, is to make a minus lambda I not invertible, so that whatever our vector is becomes in the null space, and that corresponds to going backwards, and it's just equal to a times a constant. Yeah. Oh, I can lower this some. Okay. So going on to, I kind of skipped past how you find eigenvalues themselves, right? You find the determinant of a minus lambda I, and you set it equal to 0 and you solve. This is where you may have to use quadratic formula. I wouldn't expect it on the exam, to be honest, but you should know how to do it. It just comes up once in a blue moon, and then students freak out and just put random numbers that don't make any sense. So I'm not saying that you should expect it, but I'm saying if it happens, know how to do it, okay? It's not anything more crazy or out of the park than what we've already been seeing. So. Any questions about finding eigenvalues or finding eigenvectors? Yeah. Yes. Okay. So this is the algebraic definition of all of this. All right. And now for the geometric definition of all of this. Essentially what we have is we have some, well, I'll say it in 2D for now, and then I'll talk about it and generalize it to a greater dimension as well. All right. So let's say I have a line. Okay. I'm actually going to make a copy of this and do two different things. Okay. So for this line, let's say the transformation A, or we're doing some linear transformation such that we reflect over the red line. Okay. What an eigenvalue and an eigenvector is a vector that doesn't change more than its magnitude, or it flips sign as well. So that's equivalent to multiplying by a negative, right? So if we're reflecting over this red line, what set of vectors is going to be something that's more interesting to talk about, or something easier to think about when we reflect? Something on the line, exactly, right? If it's on the line, what happens to it as we do the reflection? Nothing. So what is it multiplied by? Lambda equals 1. And this is our vector 1. That's what happens. Every time we do this transformation, it gets multiplied by 1, which is the same as saying nothing happened. Okay? Likewise, a different case is, what if it's sticking straight off? What happens to it then? Yeah, you multiply it by -1. It gets flipped exactly over, right? Think as if it's just like a flat line and it's above it, and then it flips over, right? Just -1, -1, -1, -1. So this is our vector 2, corresponding to lambda equals -1. So in this particular case, we would define C. Let's call this 2, 1. Oh, Jesus. -1, 2. So just to like put this in context of diagonalization and stuff, just writing everything out. Our first vector is 2, 1. Second vector is -1, 2. And D is a diagonal matrix with our eigenvalues. What is true of reflections in terms of eigenvalues? What are they always equal to? 1 and -1. Always, 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 right? If you're doing a reflection, there's nothing else that it could possibly be, because you're not scaling it at all. You're not rotating it at all. You're either flipping it or it's not doing anything. There's another really nice statement that says, if A is a reflection, it is diagonalizable. Always, period, forever, cool, right? So think about this in like a 3D case, right? Say I'm projecting onto like this podium here, okay? Sorry for those of you online, I couldn't get the camera to work quite right. But for reflecting over this podium, the vectors that correspond to lambda equal 1 are the vectors laying on this podium, right? We can pick any two linearly independent vectors because they just need to span this plane, which is the eigenspace. And we can just pick and choose whatever we want to do, okay? Likewise, anything sticking straight up is going to flip immediately back through it, right? Okay. So that's kind of how you can think about it in greater dimensions, but don't try to think about it too hard in any dimension greater than 3. It'll hurt your brain, I promise. So any questions on like reflections? Okay. On that same vein, let's talk about projections. Okay. Oh, damn it. Yeah. Okay. Now, if we project onto this, so we're going to actually have the same 2 vectors, right? The one that goes here, because nothing's going to happen as we project onto it. And think of a projection as just smashing everything onto this line, right? So for example, if a vector looks like this, when it gets smashed, it's going to look like that, all right? And the only other thing that we can think about is something that's straight off. So as you can imagine, this one corresponds to lambda equals 1. And which lambda does this correspond to? 0, right? Because when we project this onto this line, it just goes straight down and then at the 0, okay? All right. And this statement about reflections is also true of projections. I'm just going to copy it because I'm a little lazy. Okay, if it's a projection or if it's a reflection, it will always be diagonalizable, okay? Just a fun little aside that may come up. It usually comes up in some form, true or false, either on a homework, a quiz, on something, right? So going back to the actual question at hand, which is what is algebraic multiplicity versus geometric multiplicity, okay? So diagonalization is when all algebraic multiplicities are equal to geometric multiplicities. Okay. Any questions on any of this stuff, by the way, so far? Questions? Feel free to just raise your hand or interrupt me or yeah.
So for the like reflection.
Yeah.
So I mean, like those are the eigenvectors. Like
Yeah, these are the eigenvectors because they're the things that get multiplied by a number as we do it. Okay. Like if I had something that looks like this, okay, and it gets smashed onto here, this isn't really multiplied by a number, right? It's kind of like rotated and shrunk and turned, and that's not really something that we like to think about. It's very easy. So that's why we like to do eigenvectors in general, actually. Any other questions about this? Yeah, sorry.
What is the second eigenvector for the projection?
Oh, it's actually the same thing. Yeah. Yeah, so these are actually the same eigenvectors for both of them, just different eigenvalues, okay? That's the only difference between a reflection and a projection, okay? And rotations are also always diagonalizable, but we'll talk about that when we get to complex stuff, okay? So, algebraic multiplicity, right? Going back to the determinant of A minus lambda I. Okay, this is going to be a polynomial that looks like negative lambda raised to the n plus a bunch of garbage minus the trace times lambda plus determinant, not the trace of lambda, the trace of A times lambda. You're good. I just thought I messed something up on my side. So, all right. So what degree is this polynomial? For those of you that remember actual like high school algebra. N, right? That's the highest degree of the highest thing. So who remembers the fundamental theorem of algebra? Yeah. Yes, that's exactly it. Whatever the degree is, that's how many zeros you have, okay? So for this, you can always say, there will be n zeros. Always. Okay? And those zeros correspond to our eigenvalues. So you can always say there will always be n eigenvalues. Okay, that doesn't say distinct, does it? It says eigenvalues in general. Okay, so a good check for as you're doing these, so you can check the algebraic multiplicity because this part is algebra, right? Because there's numbers. Okay, so algebraic multiplicity is equal to, well, it's not really equal to. We say algebraic multiplicity is like for the determinant of a minus lambda I. An example would be like if we had lambda minus 2 cubed times lambda plus 5 squared, okay? This one corresponds to lambda equals 2, and this one corresponds to lambda equals -5, right? Because when we saw, the goal is to look for this at lambda equals 0, right? What algebraic multiplicity is it's this power up here, okay? So who can tell me what size matrix would make something that looks like this? 5 by 5, right? Because there's a degree of 5. Yeah, you had a question? Oh, I'm sorry. Yeah, I can change colors. Let's make it red. Is that better? Yeah, of course. Okay. So for this question, what we would say is we'd say lambda equals 2 with an algebraic multiplicity of 3. And lambda equals -5 has an algebraic multiplicity of 2. Okay. Cool. So far, so good. Any questions on this stuff? All right. So this is algebraic multiplicity. Geometric multiplicity is a step further and more complicated, but you can actually boil it down to a pretty easy way to tell some stuff. So what you do is you check. So like up here, all right, what it means for a geometric multiplicity is it means how many linearly independent vectors are in that space, okay? So if you have an eigenvalue, there must always be an eigenvector, right? Just by this definition up here, right? This definition doesn't make any sense if we don't have any vector to talk about, right? So every eigenvalue must have at least one eigenvector, okay? Otherwise, neither are a thing, okay? So there's this nice little bound that we like to write just as a sidebar before I tell you how to find the dimension or how you find geometric multiplicity quickly without doing parametric vector form or any of that garbage. So you have this bound that you will always have at least one, you always have one eigenvector. So we're looking for the dimension of the eigenspace. Okay. Okay. And this will always be less than equal to your algebraic multiplicity. Always. Okay. You can have a dimension up to your algebraic multiplicity, never more, sometimes less. And there is a statement that goes along with this that says if you have n different eigenvalues, okay, n distinct eigenvalues, what's the dimension of each of their eigenspaces? With no algebraic multiplicity, all right, for an n by n matrix. 1, right? So if that is true, everything has an algebraic multiplicity of 1. That means for each eigenspace, we have a bound that looks like this. It must be greater than equal to 1 and less than equal to 1. So what number does that have to be? 1, right? So that's the ideal why. If you have lambda equals 3 with an algebraic multiplicity of 1, it has one eigenvector. And if they don't ask you for it, you can just say that it has an eigenvector. That's a fact, okay? But how do we find the dimension of eigenspace? Well, we define the dimension of eigenspace as the dimension of A minus lambda I. No, not quite, sorry. Dimension of the null space of A minus lambda I. All right? That's what this is equal to, all right? This is equal to number of eigenvectors for a single eigenvalue. I'll just say for a lambda, okay? Okay, so for instance, if if this was my characteristic polynomial, all right, here, we have lambda equals 2, has an algebraic multiplicity of 3. And I say the dimension of the null space of A minus 2I is equal to 2. Is this a diagonalizable matrix? No, because it'd have to be equal to 3. That's this statement up here. Diagonal when all algebraic multiplicities are equal to geometric multiplicities, okay? Do we have any questions on this? Yeah. Yeah, okay. So an example would be, let me think about this for 1 second. 1, -1, -1, 1, okay? That's a bad example. So just in a very simplistic case, okay, say I have this matrix, all right? It's diagonal, so we can go ahead and pull off lambda equals 1 algebraic multiplicity of 2, okay? So when we take A minus lambda I, what do we get? We get 1 minus 1 up here, 0, 0, 0, 1 minus 1 here, 0. How many free variables does this matrix have? 2, right? So that means geometric multiplicity is 2. So that means this one's diagonalizable. So the technical process to do all this, to find the dimension of any null space, what you do, take A minus lambda I, row reduced echelon form, count pivots. Or rather count free variables. This is the same idea. Okay. And whatever your number of free variables are, is your geometric multiplicity for that lambda. Okay. Does that make sense? Okay. Cool. So I'm sure we'll do some problems where we actually look at that and stuff like that. But one other note that I will say on the note of diagonalization and all of this, I know I'm basically just lecturing when we haven't done any problems yet, but I promise we're getting there. Yeah.
I was gonna ask, what's the relationship if a matrix is diagonalizable to invertibility?
So diagonalization and invertibility are separate things. And that's why on homeworks and practice stuff, they'll ask you, hey, is this diagonalizable? Hey, is it invertible? They'll ask you both because they're kind of separate questions. The only thing that corresponds to them is if it is not invertible, okay? If it is not invertible, you have a lambda equals 0, so you know one of your eigenvalues for your diagonalization. It doesn't help much, because if you do the diagonalization, you're gonna have to find it anyway. But unfortunately, there's not a very satisfying answer there. Yeah.
What is the difference when you're finding the eigenspace and the eigenvector?
Yeah, the eigenspace is formed by the eigenvectors. It's like a basis and a column space. Okay. So your eigenspace is spanned by your eigenvectors for that thing. Okay. Does that make sense? Yeah. It's just like the steps of the two. The eigenspace is made by the eigenvectors. Okay. Cool. And one other little note. Any other questions on this? Yeah. Yeah.
So if it's diagonalizable, that means that one of, or like it has a, or like one of the eigenvalues, that means it's not invertible.
If you find it's diagonalizable and you also find that one of your eigenvalues is 0, then it is not invertible. Yeah. But that's kind of a stretch, right? There's a lot of qualifications to just get one other fact. But nonetheless, and the way that all the idea of diagonalization works, all right, is like we have C and we have D, all right? These are the two matrices we're trying to construct. Let me move this so it's a little easier to see. So let's say we're doing it for this past question up here, all right? Where we have this as our, this is our characteristic polynomial, all right? So D is 2, 2, 2, -5, -5, 0 is everywhere else, okay? So the columns of C must correspond to the eigenvectors in the columns of D, okay? So looking at this, right? How many columns does 2 get? 3. How many columns does 5 get? -5. It gets 2, right? You have to fill those columns, right? So if you only have 2 eigenvectors for 2, can you fill all 3 columns? No. So that's why it's not diagonalizable. If you don't have enough vectors to construct C, it's not diagonalizable. That's the whole motivation and idea, okay? Any questions on that? Yeah.
You're the same about eigenvectors.
So I'm not going to go into all the hard math behind that, but every eigenvalue will always be linearly independent. Eigenvector. Every eigenvector you find will always be linearly independent, such that you find like parametric vector form. Okay. If you pull them from that, they'll always be linearly independent, and then you can just stop there. Okay. You don't have to check like these are going to be 5 by 5. Say there's not a 0 entry in all 25 numbers up there. All right. It's going to be a headache to try and row reduce. But you can kind of, if you know you found them, you know they're linearly independent, and you can just be done. Okay. Yeah.
Can you expand the characters for like ends like 4 or 5?
You can.
There was like dots,
Yeah. So,
or is it just based on whatever eigenvalues?
so this will always be true for every size, but what gets complicated is like this is what is it, binomial expansion based on that sort of stuff. If you want to go back and there's not any easy relation between any of these, is what I'm saying. Essentially, what one of them is like the product of the sums of some eigenvalues and some other eigenvalues. And that's bad. We don't like doing that. It's a 2-hour class. That's asking way too much. Even some of the stuff they ask you is way too much, but I don't teach the class, so that's. Anyways, any other questions about this stuff? Yeah.
Can you explain what you were saying about like the like
Yeah. So what I'm saying here is like we have a multiplicity of 3 algebraic, right? Algebraic multiplicity corresponds to how many columns that number gets. Okay. Eigenvectors fill in these columns in the C matrix. Okay. So if we find the dimension of the eigenspace for 2, lambda equals 2, to have a dimension of 2, means it's spanned by 2 linearly independent eigenvectors. And that means we can only fill 2 columns. So the question is, what goes in the 3rd column? And that's a question that doesn't have an answer. That's why it's not diagonalized, right? How do you just make something up to put there? You don't. Okay. So whatever these are correspond to eigenvectors. In this case, like you can reorder these columns however you want, right? You have 3 eigenvectors. You can put v1, v2, v3, v3, v2, v1, v2, v1, v3, whatever you want in whatever order corresponding to that lambda. And then for this one, it's the same idea. But going back to the thought on distinct eigenvalues, you have a different one each time, right? They each get 1 column up here, and they'll always have at least 1 eigenvector, so it'll always be filled, right? Yes, question here.
Are all eigenvectors linearly independent?
Yes. Flat value, yes, always, forever. Yeah. Yeah, I didn't give it. This was just like, I didn't give a matrix. But here you can tell algebraic multiplicity. I didn't give anything on geometric multiplicity. So that's why it's just kind of open to be talked about, right? For like a specific matrix, you would have to derive the vectors from that by taking the null space of A minus lambda I forming a basis, okay? And a slight correction on that, eigenvectors will always be linearly independent if you find them correctly. Okay. So some like way that I mean by that is if I tell you that A times 1, 0 equals 2, 0, and A of 2, 0 equals 4, 0, these are not linearly independent, so that's I can only pull 1 eigenvector between the 2 of these. Okay. That's what I mean by that. As long as you know these facts and stuff like that. Because obviously this is just a scalar of each other already, so it doesn't make any more sense. Okay. Questions? Saw a couple other hands. Yeah. We don't. Yeah, we don't because I didn't give a matrix. I just gave the characteristic polynomial. Okay. So the only thing we can find from a characteristic polynomial itself is the algebraic multiplicity. You would have to have a matrix to be able to tell, or you would have to have the null space of A minus 2I. Okay. Either of those are totally valid. Any other questions on this stuff? Yeah.
Matrix have real eigenvalue and constant eigenvalue.
It sure can. All right. So I guess that kind of segues pretty nicely into complex eigenvalues. So just to build upon this stuff, this is pretty much talking about everything that this exam is on, right? Gone through eigenvalues, eigenvectors, eigenspaces, CDC, inverse decomposition, or just diagonalization. How to find algebraic multiplicity, how to find geometric multiplicity. So the only other thing besides, a couple, let me double check to just make sure I'm not missing anything blaringly obvious in between that. I'm not. The only extra thing is complex eigenvalues, okay? And these are where people make a lot of mistakes, okay? So just as another little aside that helps, that I find rather helpful, but some people don't. So complex numbers. Complex numbers. Why do we use complex numbers? I asked my studio this, so if you're in my studio, I did say this at some point. So why do we use complex numbers? To solve things is an answer. It's not the answer I'm looking for, though.
Negative root.
That solves things. So complex numbers have a magnitude and a phase. If you're an engineer, you're going to have to get used to some complex numbers, especially like mechanical airspace, any kind of signals, any kind of stuff like that. All right. Also in engineering, you stop using I and you start using J for root -1. It's only really confusing, but you'll get there. Yeah, but all that goes to say is the most important thing here is this phase, which means we're rotating. Okay. So just as like a little, again, this isn't anything that's going to be on the exam. This is more of a conceptual thing that some people find helpful, and that's why I'm saying it. For some complex number, A plus BI, all right, when you multiply a matrix times some vector, you'll get A plus BI times that vector for a complex eigenvalue, all right? And what this is doing is it's scaling by the magnitude of A plus BI, which is the square root of A squared plus B squared. And it's rotating by the arctangent of B over A, okay? So this just goes to boil down to say that any complex eigenvalue is scaling and rotating, okay? If you use the traditional rotation matrix, it's going to be scaling by 1 and rotating by whatever degree that is, okay? So for example, if I said, if I give you a 2 by 2 matrix that's rotating by 45 degrees, what are my eigenvalues? Well, they're going to be the eigenvalue that's going to be 1 over root 2 plus or minus 1 over root 2I. Because that's a 45-degree angle with a multiplicity, not a multiplicity, magnitude of 1. Okay, that's the relevance of complex eigenvalues. Okay, this is also written in engineering. Also, it's just some big letter followed by an angle theta, just because we don't like complex numbers too much, but we use them a lot. Anyways, that's for like 2 years from now when y'all are taking those hard engineering classes. Okay, so that's the idea behind complex eigenvalues and complex numbers in general. So it is still true that their solutions to A minus lambda, the determinant of that. And this is where you have to use the quadratic formula traditionally. Negative B over 2. Damn it. 2a plus or minus the square root of b squared minus 4ac all over 2a. Okay. Yeah, I know, but you got to know it. So that's how we find them. And then the process for finding eigenvalues and eigenvectors for complex numbers is exactly the same for real numbers. Okay. So any questions on any of this stuff? Any questions at all? Yeah.
They have to have conjugate, right?
Yes, these must always come in conjugate pairs because of this plus or minus right here. Okay, you're not using the square root to find a solution unless it's a quadratic that you can't factor very easily. And then you use this lovely quadratic formula to get this.
Can you talk about the negative, in the book, it took negative W over Z when you have like, A, or like, you have a 2 by 2 matrix, you have A, B, it's like negative B over A for the conjugate.
What do you mean negative B over A? For what?
Finding the
Find to actual find the eigens. Okay. Yeah, so let's do that example of, let's do 1 over root 2. Oh God, what is it? 1, -1, 1, 1. Okay, this is a rotation matrix of 45 degrees. When we take A minus lambda I, actually, I'm going to do a different matrix just to make my life as easy as humanly possible. But let's take A to be equal to 0, 0, -1, 1. Okay. What you'll find is this correlates to a rotation by what? Anybody? 90 degrees. So without finding the determinant or any of that, what are my eigenvalues? Plus or minus I heard it once. Okay, because when we're graphing on like real and imaginary stuff, here's the complex, that's 90 degrees, right? Yeah, a hard little whatever. Don't worry about it if it goes over your head, okay? But again, just to look at it, we take the determinant of A minus lambda I, which is negative lambda, -1, 1, taking the determinant. And this gives us lambda squared plus 1 equals 0. Lambda squared equals -1. Lambda equals plus or minus I. Same thing, more math, whichever way works. Okay. If you get your exam back and you did a little trick like that and they gave you shit and they count it wrong, let me know. Yeah. Anyways, so here we have our 2 eigenvalues, plus or minus I. All right. So just as a sanity check, how many eigenvalues do we have? How many complex eigenvalues do we have? 2. They're a complex conjugate pair, correct? We have one that is a complex conjugate pair, if you'd rather. It's the same idea, just don't write. Technically, each one has its own multiplicity, but they come in pairs. Okay. So is this diagonalizable? How many distinct eigenvalues do we have? So is it diagonalizable? Yes, there it is. Okay. So let's do for A minus I. Okay. So this is corresponding to lambda equals I, obviously. So we get negative I, -1. And what do we know about this matrix? It's what?
0, 0.
Why is it 0, 0?
Because you told me in studio.
I did tell you in studio. Any other guesses that aren't just from the word of my mouth, which is fine. That you are right. I know, but any other guesses? Yeah. Yeah. Yeah, you row reduce it, and what do you find out about the bottom row? It cancels. Why does it cancel?
It's
Yeah. Yeah. Complex algebra, right? So someone said something else. What was it? Exactly. You know it has a free variable, right? Because it has to. So we know the 2 rows are going to be similar, so we can just ignore them entirely. Okay. So this is kind of true for just about any, for 2 by 2, you can do this every single time. Okay, 3 by 3, it actually follows as well. All right, so now what we do is we find some eigenvector corresponding to this. And one way I like to do it is I like to flip them. So let me write this. I shouldn't use green. I know y'all can't see it. Blue, blue. So I like to flip it, -I, -1, and I make one of them negative. So I multiply by -1. This is an eigenvector. Okay. You can think of that as 1 times this plus -I times this. That gives us -I plus I, and that's equal to 0, right? So that's you could also get this from parametric vector form. It's a little bit more complicated though. Ix1 equals x2. You multiply both sides by I, and you get x1 equals ix2, which corresponds to the vector 1i. Is that right? No, I1. Yeah. I1. So these two vectors are actually the exact same thing. Which doesn't make a lot of sense, but if you multiply this one by I, you'll get here. Okay. Either of these are totally fine answers, okay? But yeah, you take, to get an eigenvector, just as a quick one and done, flip this one here, make one of them negative, okay? Another statement about complex eigenvalues is, obviously they're conjugates. So when it's true they're eigenvectors, they are also conjugates, right? So for lambda equals -I, my vector must be 1 plus I, because a conjugate is just when you make the imaginary part negative. Okay, you multiply the imaginary part by -1. Okay. Questions on this yet? Okay. Yeah. Yeah, these vectors are conjugates of each other, corresponding to the conjugate eigenvalues as well. All right. Okay. Anything else about any big picture conceptual stuff? I think I've gone over everything that's going to be on the exam. But now let's get in any other questions on any of this qualitative stuff. Yeah. Yeah, we'll do cofactor expansion, I'm sure, in one of the questions. And if we don't, I'll do it at the end. Okay. Anything else? Yes.
Okay, so one over -I is I.
So dividing by I is the same as multiplying by -I. Okay. Complex algebra is hard. There's a whole class on it here. That's a 4,000 level math class. If you take it, it'll make you a really good engineer, but you will hate your life. Yeah. Is that good?
Yeah.
Cool. I took that class. It's really bad. Not fun. Okay. What questions do we have from exams, web work, quizzes, any kind of stuff like that? Yes. Homework?
Yeah.
Okay. Question 4, you said? 7. Okay, give me 1 second. Web work always takes me a minute to pull up. So, assignments, web work.
It's the
You
last,
said 5.4?
it's the last one on 5 point.
Last one on 5.4.
They give you like a base.
Yeah, of course they do. Okay. Aha. Yes, so one thing to note about web work, in case you haven't figured it out already, is they'll always give people different numbers, and the true or false question are pooled. So it may be true that I have different numbers than what you're looking at, but it's the same sort of question. All right. So let's see if my stuff is working. It looks like it is. All right. So what this question is asking, and of course it's not looking right, because why would web work ever work? Okay. So this question says, A is a 3 by 3 whose -3 eigenspace is this, and whose 1 eigenspace is that, right? So when they give you something like this, what they're asking is to find the CDC inverse and then multiply it out, all right? Which is a headache, I know, but not really much you can do if they ask you to do it, all right? So how do you find the basis for a plane? Any ideas? Parametric vector form is a good answer. Put it in a square matrix. Sounds a little harder. I like parametric vector form though. So the way you can think about this is a single equation, right? How many free variables do you have? 2. So what's its dimension? 2. A plane has a dimension of 2, right? So which free variables are those? I'll call them y and z. All right. You can put this in parametric vector form, and you'll get a nice set of 2 vectors. Pick and choose one and the other. Totally fine. You're done. Okay. The way I prefer to do it is we know for both of them, this is actually exactly the same thing as parametric vector form. I'm just kind of solving backwards. Okay. So we know y and z are two free variables. So I just make 2 vectors where one is 0 and the other is 1, and then I switch them. Okay. So then I plug it into this equation and see what I have to have for x. So this one has negative 3x plus 8 equals 0. So x equals 8 over 3. Okay. For this one, when you plug in 1 for y, we get negative 3x minus 6 equals 0. That means x is negative 2. Boom, we have 2 vectors. Okay. It is the same thing as parametric vector form, I promise. Right. So we have 2 vectors for a 3 eigenspace. What is the dimension of our 3 eigenspace? What's our algebraic multiplicity? 2. How do we know that? We don't. It just happens that we have a 3 by 3. This is 2-dimensional. The other is 1-dimensional. So we have, from geometric multiplicity, this is the only way you can tell algebraic multiplicity, okay? You can only tell algebraic multiplicity if your geometric multiplicity is add to n, okay? So, and then this one is pretty much, they just give you a vector, right? So what you have is you construct C, which is equal to, we'll call it 8/3, 0, 1, negative 2, 1, 0, 2, negative 1, 1, right? Because this is just saying our eigenspace is the span of a vector. So that gives us our eigenvector from the basis of the span. And our D matrix, the first vector corresponds to an eigenvalue of negative 3. The second vector corresponds to a lambda of negative 3 as well. And the last one corresponds to 1. Yikes. I'm not going to do all this math right now because that's a lot. 3 times 9 times 9. A lot of calculations. But you would find C inverse from here, and then you would multiply C times D times C inverse. Okay. Does that make sense? Do you have any other questions on this? Yeah.
How did you get those x?
It's given. Who's negative 3 eigenspace and who's 1 eigenspace? Yeah. That's kind of the, you got to kind of read the question. When I like tutor and stuff, one of the things I always tell my students is the last thing you do when you solve a question is reread the questions to make sure you've answered it. Okay. Any questions on this? Yes. What do you mean one of my x-rays? One of these? The p-value is here, 0 here. Right, we have 2 free variables. We can pick and choose where we want y and z to be at any value. We can pick any harder value than 0, 1, 1, 0. But if we plug in 0, 0, we'll find the x to be 0, 2, and it's not equal. Okay. No. Okay. All right. Other questions? Yeah. Yeah, that's fine. 2000 what? Oh, geez, we're going back. Okay. Midterm 3 or midterm 3. All right. Oh, mine is not showing as something that has value there. It's not letting me download it. If you could email it to me, I'll see if I can do something there. Other questions? Yeah. Spring 2020. Spring 2022. Which question was it? 2B. Okay. The sample midterm or the actual midterm? Sample. Oh, yeah. So one of the other really important things to know for this exam is your determinant rules, right? Okay. So here, your big determinant rules, okay? If you switch rows, determinant times -1, okay? If you multiply a row, you multiply determinant by that number, okay? So going from here to here, all right? It looks like we switch the first two rows, all right? Because we get A, B, C, and we get D, E, F up there, right? And one other thing is combine rows. Does nothing. Just to like show how that works real quick. A, B, C, D. From here, we have A plus C, B plus D, C, D. That's actually not a great example, but just take this at whenever you add rows to other rows, absolutely nothing happens, okay? So all we're doing from this one to this one is essentially we're switching a row. So we multiply it by -1. So this is equal to -3, okay? Other questions? Yeah. On the last quiz, number 4. Yes, I can. Y'all have already done the last quiz, right? I'm not about to like. Okay. Okay, just making sure. One thing I will say in general about this exam is students either do really well or really poorly because it's not that many topics, right? It kind of all boils down to, can you find the diagonalization of a matrix? That's pretty much what it boils down to. So as long as you can do that, there's a few little technicalities within there, but that's kind of the overarching thing of what you can do. So 1 second, let me do this question and then. Okay, so this question out, this is from your last quiz, say is 2 by 2 and A times this 0, 0, 0, 0 equals 0, 0, blah, blah, blah. Okay, so going from this vector to here, what do we multiply by? 0. From here to here, nothing. From here to here, what do we multiply by? Who knows? From here to here, what do we multiply by? -1. So what are my eigenvalues? Does A have a null space? Why? Because you have lambda equals 0, exactly. So determine which is an eigenvector of A, okay? Is 1, 1? Yes, because you can multiply it by a number and get there. Is the 0 vector ever an eigenvector? No. Okay, is this one an eigenvector? No, because there's no number we can multiply 3 times to get -1 and 1 times to get 1, okay? And the last one, is this an eigenvector? Yes, because you can multiply it by -1 and get a multiple of itself, okay? Questions on this one? Whenever it's what?
What's the first thing you said, right?
Is the 0 vector an eigenvector? The answer is no. Sorry, that kind of got overshadowed. I also overemphasized that in studio because I was upset about it. But
Wait, no, before that.
oh, this is just multiplying this times 0 to get 0. Okay, right? That it's in the null space. Yes, it's in the null space. It's in the eigenspace for lambda equals 0. They're the same thing. Okay. All right. Other questions? I know you raised your hand. The blue. Yeah. Between eigenvalues, the only relationship between invertibility and eigenvalues is you must have an eigenvalue of 0 for it to be non-invertible. If all of your eigenvalues are non-zero, then it is invertible. Okay. It doesn't tell you much about diagonalization. Okay. If it's not invertible, you will have an eigenvalue of 0. Okay. And another little note that I don't think I said is the determinant of A is always equal to the product of your eigenvalues. Okay. Capital Pi is just the multiplying, the same way we use this sigma for sum. This is add, this is multiply. Okay. Likewise, the trace of A is equal to the sum of lambdas. Okay. Just some little facts that happen to come out of finding determinants for A minus lambda I. Okay. These are really important. And one of the things is like, I know for one of the questions they gave you like a 5 by 5 on the homework or something crazy, right? One of the ways you could have done that was if you find the trace, you find the determinant, you can find some things that multiply to be that, whatever. Oh, and trace, in case you haven't encountered that, it's the sum of the main diagonal of A. Okay. All right, what other questions do we have? Yes. 2020. Okay. So one thing I will say is for spring 2020 and for fall 21, those exams were online. So some of the stuff may just be a little different. You said same midterm 2B question 2D. Okay. Okay. So many letters and numbers that sound similar. 2D. Okay. All right. What this question says is write a 3 by 3 matrix with only one real eigenvalue. Okay. One real, such that the 4 eigenspace is 2-dimensional. Okay. So that means we have a geometric multiplicity of what? 2, right? Plane's 2-dimensional. 2-dimensional plane. It's redundant, but whatever. Okay, so we have one real eigenvalue. So can we have a complex eigenvalue here? Why? They come in pairs and there's only one spot left. Okay, so this means that we can't have any complex and it says there's no more real. So lambda equals 4 has algebraic multiplicity of 3. Okay, so is this possible? Sure, you just can't CDC inverse it, right? It's not diagonalizable. Okay. The way I like to do these is my rule of thumb is always draw at least a triangular matrix for eigenvalues, right? So we have lambda, nope, not lambda. We know what lambda is equal to. We have 4, 4, 4, and zeros everywhere else. Okay. So when we take A minus lambda I, how many free variables do we want? 2. Okay. So we know we'll always get 1, right? We get a free variable when we subtract 4 here, right? Because when you subtract it, that whole column is zeros, you have a free variable instantly. Okay, that's kind of how this works in general, actually. So what we need is we need only one of these to be free variables when we take A minus 4i. How can I do that? All 4s everywhere? Okay, if I fill this in, how many free variables do I have when I take A minus lambda I? So I subtract 4, this goes 0, 0, 0 on the diagonal. How many free variables do I have? No. 1, okay? Because this will become 0, 4, 4, 0, 0, 4, 0, 0, 0. How many pivots does this have? So how many free variables does it have? Exactly. So one solution is just to make this entry 0. Okay. Another entry would be, answer would be instead to make this last column 0 instead. Okay. You're just looking for 2 two free variables in the end. Okay, multiple ways to do it. Technically, these numbers can be whatever you want, but either this or this must be 0 and the other must be non-zero. Okay, you're just looking for two free variables in the end and three lambda equals 4 along diagonal. Questions on this? Yes.
It's saying it's the 4 eigenspace.
4 eigenspace just means that for lambda 4, we can go back and talk about algebraic multiplicity. Okay. And from talking about algebraic multiplicity, this is one of the rare cases where we can derive or geometric multiplicity. We can derive algebraic multiplicity as well. Okay. Because it says it's the only real, and you can't have a complex because there's only one space left because that's a dimension of 2. So there's one more space. Doesn't the algebraic only equals to the geometric multiplicity when it's diagonalizable. Does that answer your question? Cool. Other questions on this? Yes. So that is geometric multiplicity, not algebraic. So algebraic multiplicity talks about the free variables when we take a minus 4i. It doesn't talk about how many times it happens algebraically. Okay. And a good way to remember the difference between algebraic and geometric multiplicity is geometry happens in space. It's a plane, it's a vector, it's planes, it's 3 spaces, 4 spaces. Algebra is numbers. Okay. Your numbers correspond to your eigenvalues, which correspond to your algebraic multiplicity. Your geometric multiplicity corresponds to your vectors in space. Okay, yeah. Oh, I took a minus 4i. Yeah, to find the eigenspace. Okay. Other questions on this? Yeah. To find the D matrix, you just have to find your eigenvalues, whichever method proves best. It's kind of contextual. Do you have a specific problem for that you were looking at? For here? Problem. Did I already do that one or this one? Okay. D was found here just because we knew our eigenvalues. We just plot them on. Okay. It was given, I believe, right here. Yep. 1 eigenspace and -3 eigenspace. So that corresponds to your lambda. Okay. Because it has a dimension of 2, so you know also algebraic multiplicity of these 2, which fills in the 2 spots. Okay. Cool. Yeah. It means multiply by all. It's sum. Remember, if you've taken calculus, right? These lovely infinite sums here. These mean add. These mean multiply. Very few of you will see this again, but I just find it helpful to write it out. Okay. It's just like shorthand notation, like I'm sure you've seen plenty of times. Yeah. Spring 2022. Okay. No, shit, where'd it go? Oh, this one. Oh, -3. It's 3 times -1. So that's why we like this rule here, okay? Because what we're technically doing to combine rows is we're multiplying this row by -4, adding it up, and we add rows, technical definition of when we don't. And then we go back and we divide this by -4. So that means we're multiplying the determinant by -4 and then immediately dividing it by -4. Okay, so that's why nothing happens. Okay, yeah. Yes, I will go over cofactor expansion. Yes. All right. I'll get you next. I promise. All right. So A equals, we'll call it A, B, C, D, E, F, G, H, I. Okay. Cofactor expansion is probably the most helpful tool to actually find like eigenvalues. All right. It's in my opinion, the fastest way to do a determinant. All right. So what you do is I like to pick the row or column with the most zeros. Rule of thumb. Okay. It's cofactor, expansion. Number one, pick row or column with the most zeros. Okay. What you do from here is you must always, always, always draw this little phantom matrix. Okay. It will always be the same size. In this case, it's a 3 by 3. Okay. What you do is you put a plus in the top left, and then you build out and you draw minuses, pluses, and then minus, minus, plus. Okay. This is the same thing as I believe -1 to the row plus column. Okay. What this means is as we move along a specific row, okay, as we move along a specific row, like for instance, if I move along ABC, okay, it's going to be, what's going to happen is it's going to be A times the determinant of some matrix, which I'll fill in a second, minus, and we get the minus from here. So this is plus A minus B plus C times some stuff, okay? We follow this, and every time you do this, like if this is a 4 by 4 to start, when we take determinants of our 3 by 3s after, we redraw this and then take it from that matrix after that back, okay? So in this particular case, what it's going to look like is determinant of A equals A times the determinant of what we call the minor. And what the minor is if we take our position here and we cross out the column and we cross out the row, what do we have left? Well, in this case, we have E, F, H, I. Okay. And then we take the minus from here, minus B times whatever B's minor is. So that's here, times the determinant of D, F, G, I, and this will be plus C, because we get the plus from here, times the determinant of D, E, G, H. And then from here, we use determinant rules on 2 by 2s to kind of do those quickly. All right. Questions on this? If this is a 4 by 4, each of these matrices would be 3 by 3, and we'd have to do it again. It'd be a headache and a lot. All right. Yeah. Yeah. So what is true is any row or column you pick, you'll always end up with the same place. Yeah, you could absolutely have gone across the first column, or the third row, or the second row, or you have to follow that row or column you pick. And you have to follow whatever these pluses and minuses are. Okay. Cool. All right. What other questions do we have? Yes.
Go for
5.2, problem 3. Do I already have that pulled up? No, I do not. 5.2, problem 3. Ugh. Dude. Do we have to?
just like
I'm kidding, of course. All right. Oh shit. Yeah, use a calculator. That's okay. Oh, of course it doesn't copyright either. Yeah, I know. Oh no. You get this huge paragraph of text, and then you get all of these fun things down here. All right. So okay. So what this question asks is find your eigenvalues and find dimension, okay? The process for this is a headache, right? But we have to do it. The way I would pick is I would go across this row first after we take A minus lambda I. Okay. So I'd get minus lambda times the determinant of minus plus minus plus. Okay. So that's plus negative lambda. And the determinant of 4 minus lambda 0, negative 6, negative 6, negative 2 minus lambda 6, 4, 0, negative 6 minus lambda. And then from here, you continue the cofactor expansion. And eventually you'll get to a point where you have eigenvalues. You can tell right off the bat, you can have a lambda of 0 though. Okay. So if you can tell you have an eigenvalue of lambda of 0, that means your determinant is 0, right? And our trace is equal to 4 minus 2 minus 6, which is equal to negative 4. So I can already tell you what the other eigenvalue is going to be. The smaller eigenvalue is negative 4. The greater eigenvalue is 0. Because if I'm not mistaken, I believe this one has a complex eigenvalue. Complex eigenvalue. Okay. This is incredibly a headache. This sucks. If they ask you to do this on the exam, I will be sending an email as well because that's absolutely ridiculous. I don't know how you're supposed to do this and 6 other questions in an hour 15. So know how to do it. And I'm not going to say don't expect it on the exam, but don't expect it on the exam. Anything this hard at least, okay? Yes. Yes, all right, volume. It's incredibly straightforward. Volume equals determinant of a matrix constructed by your side vectors. Okay. It's as simple as that. Okay. For a 2x2, if it asks for a triangle, you have 2 vectors and then you just have it. One question that they like to ask is they like to give you 3 points. And then they ask, what is the area of the triangle spanned by these 3 points? The way you do that is you have to find vectors from points. So what I like to do is given, I'll say 0.1, 0.2, and 0.3. To find vectors, you always just subtract points, right? You get from one point to another. So I'll call vector 1 equals 0.3 minus 0.1, and vector 2 equals 0.2 minus 0.1, okay? Then you find the determinant of V1, V2, and you half it because it's the triangle, not the full parallelogram, okay? This will give you your area. Something about areas, can it ever be negative? No, so we put a nice absolute value here. Which technically makes this a nonlinear question, but whatever, it's linear algebra. Yes. A what? Which question was it? Yeah. Okay, you said from last year's? From spring 22? Okay. This from the sample. And it was like adding eigenvalue. Problem 7, this one of the graph. Yeah. All right. So I graded this problem last year, and let me just say, woof. But yeah, you gotta know how to do it. Now, come on. Here we go. All right. Okay, so this question says they're all unrelated. But let's actually do B real quick. I'll do B after this one just because it's nicer to get determinant rules. This one says, consider the matrix A whose 1 eigenspace is the solid blue line and whose 2 eigenspace is the dotted red line below. Find 7, 3. So 2 eigenspace is the span of the vector. That's 4, 1. And 1 space is the eigenvector that looks like 3, 2. Okay. So the whole reason we do linear algebra is so we can apply one thing. What is that thing called? Linearity. The whole point of linear algebra, okay? What is linearity? Linearity is that whole stuff you learned with bases. right? Or subspaces particularly, okay? The whole idea is A of vector 1 plus vector 2 is just equal to A of vector 1 plus A vector 2, okay? Something to note is for classes that you've taken in the past, something that's more familiar to this, is like derivatives are linear, integrals are linear. Things like that, we can break apart into methods like this that make them incredibly easier to solve, okay? This is why we use linear algebra in differential equations. What we actually do, we find a general solution, we use a linear approximation, and then we specify it with a particular solution. Which I know that's a lot of really high buzzwords at once, but you'll get there, I promise. Yes, so what we have here is they say to find 7, 3 without a matrix A. There's two ways you can do this. The hard way is to find C, to find D, and then to find A equals C times D times C inverse, and then multiply that by 7, 3. That's a lot of work, right? An easier way to do this is to say 7 over 3, 7, 3 is just equal to 4, 1 plus 3, 2, right? So when we take A of 7, 3, it's equal to A times 4, 1 plus A times 3, 2, and A times 4, 1, since it's in the 2 eigenspace, that's 2 times 4, 1, and 3, 2 is in the 1 eigenspace. That means this time plus 1 times 3, 2, and this becomes 8 plus 3 is 11. Oh, fuck, did I? Yeah, I did. Yeah, I did. Okay, yes, I did. My bad. So this is 1 and this is 2. So that becomes 10, 5. Okay. And that's how you, this is the easy way to solve this question, right? So multiplying out 3 2 by 2 matrices that you find, and you have to find an inverse, then you multiply it by a vector. Well, ew. Okay. Questions on this one? Yes. Because there's not an easy way to get there, right? Can we multiply 4, 1 or 3, 2 to get to 7, 3? Don't think too hard. The answer is no. Otherwise, we could just take like this and then we could multiply it like that, right? Because the other part of linearity is A times some constant times a vector is just that constant times A times that vector. Okay. This is why we like linearity in linear algebra. This is why we use it. This is why we teach it. This is why it's important to engineers in general. All right. Engineering is just problem solving with differential equations. Differential equations is just calculus and linear algebra. So yeah, we're going to the next 4 years of your life. Yeah. This question is from last year's sample midterm, was it? Yeah, sample midterm, question 7. Okay. Just to go over part B on this really quick. Determinant A is 5, determinant of A, B inverse is 10. For powers and multiplication, what we can do is we can take the determinant A times determinant of B inverse. Okay. Determinant of B inverse is the same thing as 1 over the determinant of B, or determinant of B all over raised to the -1. So this is equal to 10. So this says 10 is equal to determinant of A, which is 5, over the determinant of B. So what is the determinant of B equal to? 1/2. Okay. So this says another thing to note is the 4 by 4 matrix. So if we have the determinant of -2 times B, how many rows are we multiplying by -2? 4. So this is equal to -2 raised to the 4th times the determinant of B, which is equal to 2 to the 4th is what? 32? 16? Oh shit. 16 times 1/2, which is just 8. Okay. You should expect some question like this. They love giving these and they love making them look harder than this, but you should be able to do it nonetheless. Any questions on this? Yeah. It came because we're doing it 4 times because it's a 4 by 4. So we multiply 4 rows by -2. So it's, yeah. Yes. Oh, yes. Apologies. Oh, yeah. Oh, haha. Here's this fun question that was on the homework that gave a lot of y'all a headache. If you want me to go over it, I can, but I'm gonna do this other question first. That's a very common question, and you should know how to be able to do something like that. All right. So this one says A is C times that matrix times C inverse of C has two columns of vectors. Given X and Y in the picture below, draw the vectors AX and AY. Okay. How do you break this down? Well, you break this down to the same concepts of linearity. The whole goal is to write X in terms of some number times V1 plus some number times V2 to be able to then transform it accordingly. Okay. So here we have X, and they've already drawn a grid for us, which is very nice. So this is -2 V2 and -2 V1 to get there. So we have X equals -2 V1 minus 2 V2. And X corresponds, V1 corresponds to an eigenvalue of 1/2. And V2 corresponds to an eigenvalue of -1. So what this becomes is given X and Y, draw the vectors AX and X. Okay. So what this becomes is V1 times 1/2. So that becomes -1 over, -1 V1 minus 2 times -1 plus 2 V2. The way we draw that, let's clean this up a little bit. -1 V1 plus 2 V2. So that makes this vector AX. Does that make sense? Questions?
That's not.
Oh, shit. Interesting. I see. My apologies. Oh, I think you emailed me all. Oh, you emailed the entire midterm. Okay. What question is it? Third problem. Okay.
I want to ask
The whole third problem?
Yes.
excuse me.
Yeah, go ahead.
Yeah, I want to ask, where do you get your -2s? I'm a little bit confused by that.
Yeah, so on this one, where you get those -2s, this is already gridded out for you, and here's 1 times V2. So here's -1 V2, -1, -2 V2. And then V1 goes this way. So we have -1, -2 V2, and they line up such that that is where we have X.
All right, good. Thank you.
Yep. Sorry. If you guys have any more questions about anything that I've missed, please feel free to email me, post some PLs, anything. I'll keep going for a few more minutes and then I'll call it.
That's how I.
Okay. So this is a good question of actually application. Is this your question? Okay. Just C and what? C, D, and E. Okay. C, D, E. Okay. This was what I was talking about with the complex stuff. This is what this is, okay? So what you'll find is I believe you'll get eigenvalues of, what is it, 2 plus or minus 2i, okay? Okay, just to skip past these. Matrix C, which is similar to A and represents a this is not anything you have to do. Okay, this is if we actually taught complex numbers, which would make too much sense. Yeah, thank you. But whatever. So if you are curious on how to do it, scaling factor is the square root of 2 squared plus 2 squared. Rotation is arctan of 2 over 2, which is 1. Arctangent of 1 is pi over 4. Cool. All right. Any other big questions before we call it? All right, cool. If you have any other questions, I'm going to hang out for a minute. And online, I'm sorry I didn't check most of y'all's questions. Just send me an email or post on Piazza. And for those of you watching the recording, I hope the exam's going well, whatever semester it may be.